All right, let's go ahead and open up to page 147. We're going to start the next section today. You're going to see how it's not really anything new. We're still talking about graphs and x-intercepts and all those fun things. But this section is going to be a little less math work. Okay, not a lot of algebra, for instance. We're going to be kind of identifying different properties about graphs, kind of using some terminology or vocabulary to help us describe those. So it's not really essentially a math type section, it's more of a vocab type section and becoming familiar with certain terms. Okay, so we'll kind of see how this one goes. Bless you. Taking a look at the boxes at the top, we're going to try to describe or classify the different types of polynomials that we have here just based off the way the graph looks. Now we've kind of already discussed some things we can look for to help us determine what type of polynomial we have. But if the directions continue to say that I want you to focus on the zeros or the x-intercepts to help you describe the type of graph that we have. So I think in the past we've talked about those humps and bumps. We're going to get into that today too. But specifically for this direction, we're going to take a look at the x-intercepts. So maybe taking a look at f of x, our first graph here, can you give me the name of that type of polynomial based off the x-intercepts, the zeros? What do you think, Tori? How do you know? All right, so we're going to bring back the whole multiplicity concept from the last section, okay? So if we can identify the zeros, the x-intercepts, we can then identify their multiplicities, how many times those zeros are factors, how many times they go in evenly. So notice how this x-intercept, the graph goes straight through, which means it's a multiplicity of 1, like Tori said, and this x-intercept just touches or bounces, which means a multiplicity of 2. And if we were to add the 1 and 2 together, we would get 3, which is signifying a cubic, okay, power of 3 polynomial. So we're going to use some type of synopsis or conclusion with those types of characteristics in our description. So we'll say, you can write down whatever you want. The two x-intercepts have multiplicities of 1 and 2. Which add to 3. So the polynomial is cubic. Something like that. Whatever your description or justification is, I'm sure it would be fine. All right, so maybe using some similar logic, let's go ahead and check out G. I see pencils moving, which is good. I'm wondering what you're writing. Any takers? Go ahead, Hannah.
The 3 x-intercepts have multiplicities of 1, 1.
Okay, so those are the ones. And 2, good, okay.
And so they add 4, so it's a quartic.
Quartic, good, kind of like quarter. So the 3 x-intercepts have multiplicities. I abbreviated because I ran out of room, but multi just means multiplicities. Multiplicities of 1, 2, and 1, which add to 4. So the polynomial is quartic. Okay, so we don't really know what the equation is. We could write the equation though, because we know what the x-intercepts are. We can then go ahead and write it in factored form. So we know in the end we would somehow have an x to the 4th for this graph and an x to the 3rd for the first one. What about h? Anybody want to give it a shot? Go ahead, Hannah.
There's 3 x-intercepts, and 2 of them are multiplicity and 2 and 1 of them is 1. So they add 5.
Quintic. Good. Okay, so the 4 x-intercepts, not 4, sorry, 3 have multiplicities of 1, 2, and 2, which add to 5. So the polynomial is quintic. Perfect. So somehow we would be anticipating an x to the 5th power in the equation. If it was in standard form, like no parentheses, everything expanded. So far, so good. How are we doing with identifying? Pretty easy off the multiplicities? Good. All right, so let's go ahead and talk about identifying a little bit more, not necessarily just the type of function we have, but certain properties or characteristics that these graphs display. So we're going to be bringing in a lot of concepts from previous sections and even units that we've discussed, like domain and range, and maybe being above or below x-axis, increasing or decreasing. This section really kind of ties everything together that we've been talking about in terms of graphs and characteristics. So we're going to go ahead and use this graph to help us with these particular characteristics that we want to identify. Let's go ahead and tackle domain and range first. All right, so domain are all the x values that you could plug in that would give you a point on the graph. I think in the past we talked about dragging our pencil to kind of help us determine that based off the graph itself. So if you were to drag your pencil left or right across those x values, what would you get as your domain? Yeah.
Negative infinity to positive infinity.
Okay.
Numbers.
All real numbers. Okay, so you can actually give the interval negative infinity to positive infinity. You can give the mathematical symbol for all real numbers, that double-stemmed R. Either one of those is fine. Good. All right, what about range? Instead of dragging pencil left or right, what if you dragged it low to high? Good, Brianna? All right, and what about the grouping symbols, like brackets or parentheses? For both? Okay. Can my pencil touch -4? Yes. Okay, so let's go ahead and change that to a bracket. There we go. All right. The next one, what about left and right end behavior? We briefly talked about this in the multiplicity section. We're definitely going to look more into it when we get back from break, okay, in the next section. Actually, maybe even Wednesday. Who knows how this goes, okay? But left and right end behavior, we're just going to think about if we were to trace just the left side, what does the graph do? If we were to just trace the right side, what does the graph do? We want to describe literally the behavior. How is it acting? Okay? And when we talked about this in the last section, it looked similar to the continuity descriptions that we've done in the past. So as x is approaching something, what is the graph or the y value approaching or doing? So let's go ahead and tackle the left end behavior. If we're going to trace the left side of the graph, the x's are going to get more and more negative, okay, if you think about your number line. So as the x's get more negative, what are the y values doing? Or what's the graph doing in terms of the direction it's traveling? The further we trace to the left, the y values or the graph, what would you say? Yeah. It's going up forever, meaning the y values are increasing towards positive infinity. Okay, so that's the left end behavior. For the right end behavior, if we trace forever to the right, the x values are getting more positive. So as the x's approach positive infinity, what do the y values do? How's the graph behaving? Yeah, it's approaching positive infinity as well. Yep. So far, so good. We hanging in there? All right. What about next one? Identify the intervals where p of x, okay, the graph, is less than 0. What should we be looking for that case? Remember, p of x, g of x, h of x, whatever it's named, those are like y values. So we want y values that are less than 0. Where do those happen? I'll give you guys a second to wake up this morning. I see pencils moving. I just want to know what you're writing. Yeah?
-3 to 0, 0 to 3.
Well, okay, good. How'd you get those?
Because they are the points under the x-axis.
Below the x-axis. Good. Below x-axis. Perfect. Y values that are negative, we got below the x-axis. So Dylan was pretty good with his description there. At first glance, it looks like from -3 to +3 you're below, but you got to be careful at 0 because you are on the x-axis at that spot. So we got to kind of skip over that location. So we'll skip over it using parentheses. Good. What about the flip side? Okay, p of x or the y values are greater than 0. Hopefully we can reason through that means above x-axis, kind of the opposite of the one we just did. Any takers on those intervals? Let's see, how does -infinity to -3 sound for the first one? Okay. And then 3 to infinity. We doing okay? All right, last but not least, what about where we are increasing? If you were to trace the graph from left to right, just like you read a book, where would your pencil be going up? Can we describe those sections? Good, Brianna?
-2, 0, and 2 to infinity.
Brackets, parentheses, what's going on?
Parentheses.
Parentheses for all of them. Good. Okay, so increasing, decreasing, constant, those are always parentheses. I think we talked about, because if you were at -2 right here, how can you tell me for sure if you're going up or down, right? If you're at a low point. Okay, so those look good. What about decreasing? If you were to trace it left to right, where would your pencil be going down? Good, Hannah?
Second infinity 2 and 0 to 2.
You mean -2? Negative infinity, -2?
Yeah, I didn't.
That's okay. And then 0 to 2. Good. Checks out. We doing okay? Kind of review a little bit, right? Okay, we're bringing all of it back because we're talking about characteristics of graphs. Perfect. All right, so not necessarily anything new in terms of terminology, at least on those few examples. We are going to take a look at some wording or phrases that you might be familiar with, but we're going to formally define them mathematically. I'm not saying that you have to use these definitions all the time. Okay, this is just how they are kind of described in the math world. So you've probably heard of a maximum before. More commonly, you can think about it as a high point. Okay, but in terms of a formal definition, a maximum, if you really think about what is happening at a high point right there, the graph is kind of changing the direction it's traveling. Notice how in order for me to create a high point, I need to first be going up, and then I have to change direction and go back down. Okay, that change is what's causing a high point to be created. So formally, we're going to say a maximum is a point on the graph where the graph changes specifically from increasing to decreasing. You have to be going up and then change to go down to create a high point. So we'll say changes increasing to decreasing. So think about drawing the graph left to right without lifting, or like you would read a book. And whenever your pencil changes from going up to going down, you can identify a high point, aka a maximum. So I kind of jumped the gun a little bit and showed you where one of them is located in that first spot. So we'll say we have a relative max. Okay, we're eventually going to talk about an absolute maximum. We'll get there in a second. Relative just means kind of a high point, any high point on the graph. Where does that relative max happen? Can you describe its location? Yeah.
1, 4.
1, 4. Okay, we'll give the ordered pair. Looks good. Can you find any maxes, aka high points, where your graph changes increasing to decreasing on the next one? If you were to trace it left to right, where would your pencil go from up to down? Good.
-2, 6.
Let's see, -2, 6. So this one looks good. Okay. Notice how we go from increasing to decreasing. We have that change. Do we have any other ones? Any other spots where we change direction from up to down? You see another one?
2,
Yeah.
0.
2, 0. Yep. It's a little small, but you do go up to down if you were to trace it. And the point 2, 0 looks good. Okay, so maximum, you've heard about it before, you're used to it, it's just a high point, but formally described, defined, you're changing an increasing to decreasing type of motion. Okay, so a relative minimum, if we don't put too much thought into it, it's going to be fairly similar. This time we're just going from decreasing to increasing. Okay, the change is a little bit different, specifically switched. So formally, a minimum is a point on the graph where the graph changes, decreasing to increasing. All right, so go ahead and trace it left to right. Where does your graph change from going down to going up? What do you think? At least for the first one. Yeah. 3, 0 looks good. What about the second one? Yeah.
1,4.
Say it again.
Oh, I thought we were talking about the first. Never mind.
That's okay. 1, 4 would be a max. Yep.
-4, -2, or -2, -4. Sorry.
-2. -4 looks good. I get them switched all the time, Dylan, no worries. Is there another one? Yeah.
2, -4.
2, -4. Good. How are we doing with the terminology and the maxes and mins, right? Okay. All right, so we do have other types of maxes and mins that we can classify. So relative just kind of means a generic point on the graph, a high point, a low point. But we can also be a little bit more descriptive. For instance, maybe we can identify an absolute minimum, like the lowest point on the graph, okay, or perhaps an absolute maximum on the next page, like the highest point on the graph. So we're not just looking at a general sense anymore, we're trying to find the highest and the lowest. So formally we'll say for an absolute minimum, the lowest point or points, okay, that's a little interesting. Sometimes you can have more than one lowest point. The lowest point or points on a graph All right, so take a look at the first example. Okay, it's kind of the same graph as the one above over there. Can you identify where the lowest point on that graph would be? Any thoughts? This one's a little tricky. Maybe we'll go over to the next one. Okay. On the second graph, can you find the lowest spot on that graph? There aren't any other points lower than it. Yeah. 2, -3. Okay, so the absolute minimum is at the point 2, -3. Notice how at that point there are no other points or sections of graph below it. So what about the previous one? What do you think, Tori? Why?
Because that's as far as you can go.
Okay.
Stop it somewhere.
Exactly. Notice the arrow means you're going to keep going down and down and down forever. So you're not really going to have a lowest point, or you could think about it as negative infinity. We're not necessarily going to write it as a point because technically you'll never reach negative infinity. You'll never have a point there. We'll just simply say there's no absolute minimum. Okay, so even though the same graph in the middle of the page had a relative min, okay, there was a low point on the graph, there is not an absolute minimum. There's no lowest point on the graph. Can we see the difference between the two? Even though they're both technically minimums, they're two different types. Okay, a low point versus the low point. What's interesting is if you look at the this example in the middle of the page, we labeled these as relative minimums because they are low points on the graph, but technically aren't these the lowest ones as well? Okay, so we could be a little bit more descriptive. If you wanted to cross out relative and write absolute there, you could. And notice how you have more than one absolute minimum. Okay, there is more than one point that is the lowest on the graph. They have the same y value, okay, but you do have more than one point. Let's go ahead and try to tackle absolute maximum. Similar or same idea, this time we're just looking for high points. So we'll say the highest point or points on the graph. Take a look at the first picture. Can we identify a high point, or not a high point, that would be relative max. What about the highest point? Absolute maximum. Yeah?
-2, 6.
-2, 6. Looks good. Okay. Notice how we would have a relative max, okay, at 2, 0. Okay. That's another high point, but it's not the highest. Okay, we're just looking for absolute in this case. What about the next graph? The highest. Yeah. Exactly. We have some arrow, in this case specifically 2, but we have at least one arrow that's signifying we're going to go up forever. So we're not necessarily going to reach a highest point. So no absolute maximum. Okay, are we okay with the difference between the two? Relative versus absolute. Relative is just general, okay, a high point or a low point. Absolute is more specific, the highest or the lowest. There's a difference between the two. All right, we're going to end there today because I'm pretty sure point of inflection and the terminology of concavity is all new to us. So we're going to save that tomorrow because the bell's going to ring in a little bit.